In this video, we will explain the critical path method, which is a fundamental project management technique used for planning, scheduling, and managing projects. We will explore the following elements of the critical path method: network diagram, early start time and early finish time, late start time and late finish time, and total float. We'll use an activity table, also known as a precedence table, to list the activities for an example project that we will use to explain the critical path method. Alongside the activity table, we will plot a simple network diagram. The first activity is A, which has no predecessor activity and has a duration of 2 days. The second activity is B, which has a predecessor of activity A and has a duration of 3 days. The next activity is C, which has a predecessor of activity A and has a duration of 1 day. Activity D also has activity A as a predecessor and has a duration of 5 days. Activity E has 2 predecessors, activity B and C, with a duration of 7 days. And finally activity F, with 2 predecessors, activity D and E, and a duration of 3 days. To determine the project's total duration, we must first identify all paths within the network diagram and sum the durations of the activities along each path. The path with the longest cumulative duration will represent the overall project duration. Our plotted network diagram reveals 3 paths. Nodes A, B, E and F make up the first path. The total duration for this path is 15 days. Nodes A, C, E and F make up the second path. The total duration for this path is 13 days. Nodes A, D and F make up the third path. The total duration for this path is 10 days. In this example, path A, B, E, and F has the longest duration at 15 days, making it the project's total duration. This path is also known as the critical path because any change to an activity within it will directly alter the project's overall completion time. Project execution frequently requires adjusting activity start times. To maintain effective scheduling, it's crucial to determine an activity's maximum allowable delay without affecting the project's duration. To better visualize and explain this information, we'll adapt the network diagram. We'll convert the circular nodes into square boxes where the activity's duration will appear at the top and its name in the middle. The next step involves calculating the earliest time an activity can start, ES, and the earliest time an activity can finish, EF. This can be done through a process known as forward pass. We will start by entering 0 as the ES of the first activity. The EF will be the ES plus duration, which would result in 2. For the next activity, activity B, we will bring the EF of the predecessor into the ES. The EF will be the ES plus duration, which would result in 5. Activity E cannot start until both activities, B and C, are finished. Thus we need to compute the ES and EF for activity C first. For activity C, we will bring the EF of its predecessor, activity A, into the ES. The EF will be the ES plus duration, which would result in 3. We are now ready to fill in the ES for activity E. But there is a small catch here. Since activity E needs both activity B and C to be finished first, we will have to select higher EF of activity of B and C into the ES of activity E. In this case, we enter 5 into the ES. The EF will be the ES plus duration, which would result in 12. Activity F cannot start until both activities, E and D, are finished. Thus we need to compute the ES and EF for activity D first. For activity D, we will bring the EF of its predecessor, activity A, into the ES. The EF will be the ES plus duration, which would result in 7. We are now ready to fill in the ES for activity F. But there is a small catch here. Since activity F needs both activity E and D to be finished first, we will have to select the higher EF of activity of E and D into the ES of activity F. In this case, we enter 12 into the ES. The EF will be the ES plus duration, which would result in 15. 15 is the earliest that activity F, which is the last activity, can be finished. This is the same as the 15 days of project duration that was calculated earlier. After the forward pass, we need to execute the backward pass to calculate the latest time an activity can start, LS, and the latest time an activity can finish, LF, without impacting the project duration. The latest time that activity F can finish without impacting the project duration is 15, so we enter 15 into the LF of activity F. The LS will be the LF minus the duration, which would result in 12. For the next backward activity, activity E, we will bring the LS of activity F into the LF. The LS will be the LF minus the duration, which would result in 5. We can now bring in the LS of activity E into the LF of its predecessors, B and C. The LS of activity B and C will be the LF minus the duration, which would result in 2 and 4. We will bring in the LS of activity F into the LF of its remaining predecessor, activity D. The LS of activity D will be the LF minus the duration, which would result in 7. The remaining activity A has 3 successor activities which are B, C, and D. For the backward pass, we need to bring in the lowest LS of the successor into the LF of activity A. In this case, we will bring the LS of activity B. The LS of activity A will be the LF minus the duration, which would result in 0. We have completed both the forward and backward pass. The next step is to calculate the total float, also sometimes called the total slack. It is the maximum amount of time an activity can be delayed from its early start, ES, without delaying the project's overall completion date. Total float can be calculated using either of these two formulas: total float equals late start, LS, minus early start, ES, or total float equals late finish, LF, minus early finish, EF. Both formulas will provide the same answer. Using either of the formulas, we can fill in the total float, TF, of each activity. 0, 0, 0, 0, 2, 5. Note that the TF of the critical path A, B, E, and F is always 0. That means that any change of the scheduled activities on this path will impact the project timeline. Activity C, which is not in the critical path, has TF of 2. That means that the maximum this activity can be delayed without impacting the project duration is 2 days. Activity D, which is also not in the critical path, has TF of 5. That means that the maximum this activity can be delayed without impacting the project duration is 5 days. This concludes our video on the critical path method. If you have found this video useful and would like more videos like this, please visit pmstudies.com. We also provide one-on-one and online class training for PMP, CAPM, and ACP exams. We are adding new videos every week. Please click on the subscribe button shown below to be informed when we add a new video. The playlist shown below gives you a list of related videos to watch. Thank you for watching this video.